Welcome to Software Architecture. This is lecture 8. We will be discussing on performance. This is Professor T. Freed Muhammad. What is performance? Performance general scenario, tactics for performance, a design checklist for performance, and last not least, we'll be discussing how we have concluded learning in this lecture. So what is performance? Performance is about time and software systems' ability to meet timing requirements. When events occur, interrupts, messages, requests from users or other systems, or clock events, marking the passage of time, the system or some elements of the system must respond to them in time. Let's look into this with an example in more depth, and we'll use a clinical system as our running example for this lecture. In a clinical system such as electronic health records or real-time patient monitoring platforms, performance directly impacts patient care and safety. These systems must handle high volumes of data from lab results to imaging studies while ensuring sub-second response times for critical tasks like retrieving patient histories or alerting clinicians to anomalies. Architectural decisions such as optimizing database queries for fast retrieval of time-sensitive data or leveraging in-memory caching for frequently accessed patients' profiles are vital. For example, a poorly designed EHR or electronic health records that lags during peak hours could delay diagnosis or treatment, risking patient outcomes. Performance here is not just a technical metric but a lifeline, requiring architectures that prioritize low latency, fault tolerance, and seamless scalability to accommodate fluctuating demands such as emergency room surges or telehealth consultations. To meet rigorous demands of clinical environments, architects employ specialized strategies. Distributed architectures, such as microservices, allow modular scaling of components like prescription management or imaging analysis without overloading the entire system. Asynchronous processing can decouple resource intensive tasks such as AI driven diagnostics or batch processing from a real time workflows, ensuring UI or user interface responsiveness for clinicians. Caching mechanisms like storing recent patient virtual and vital or lab results at the edge on hospital servers, reduce reliance on centralized databases, and minimize latency. Database sharding, partitioned by department or patient cohort, prevents bottlenecks during concurrent access. Additionally, compliance with standards like HIPAA or GDPR introduces performance trade-offs. For instance, encryption of patient data at rest and in transit adds overhead, necessitating hardware acceleration or optimized cryptographic algorithms to maintain speed without compromising security. Balancing performance with regulatory and ethical requirements is a unique challenge in clinical systems. For example, real-time analytics for ICU monitoring demands ultra-low latency but must also ensure data integrity and auditability, which can slow processing. Over optimizing for speed might lead to brittle systems that fail during unexpected loads, such as pandemic-driven spike in telehealth usage. Trade-offs also arise between interoperability and performance. Integrating third-party systems, lab equipment, or pharmacy databases via APIs can introduce latency. Yet spoiled data undermines care coordination. Architects must also mitigate risks like single points of failure. A crash server during surgery could be catastrophic. Solutions like active redundancy and edge computing for localized processing help, but they increase complexity and cost. Ultimately, clinical system performance hinges on iterative testing, adapting, scaling, and patient centric ethos that prioritizes reliability without compromising compliance or usability. Performance general scenario. Let's look into this with the same clinical system as our running example. In clinical architectures, the source of a performance related event is often a user, such as clinician querying a patient's electronic health record, or an external system such as a lab device transmitting test results. The stimulus is the specific action or condition triggering the system, such as high priority request for real time patient vitals during surgery or a sudden influx of telehealth requests during the public health crisis. The artifact, the system component directly affected, could be a database handling concurrent queries, an API integrating imaging systems, or real time alerting module processing streaming data. For example, when a clinician accesses a patient's radiology images, the stimulus image retrieval request targets the artifact imaging storage subsystem, which must prioritize speed and reliability to avoid delays in diagnosis. The environment defines the state of the system when the stimulus occurs. In clinical settings, this could range from routine operations such as scheduled patient check ins to high stress scenarios such as emergency room overloads or ICU monitoring during a code blue. Environmental factors like network latency, hardware constraints, outdated hospital servers is an example, or regulatory environments such as data encryption for HIPAA compliance shape performance outcomes. For instance, a cloud based EHR system operating in a rural clinic with limited bandwidth faces different environmental challenges than one in the metropolitan hospital with robust infrastructure. Artifacts like edge computing, nodes, or hybrid cloud database may be deployed to adapt to these environmental constraints, ensuring consistent performance despite variable conditions. The response in the system's behavior triggered by the stimulus, such as delivering patient's data within milliseconds, generating and alerting for abnormal lab results, or syncing records across distributed systems. Response measures quantify performance success like sub-second latency for clinical transactions, 99.99% uptime during peak loads, and less than 1% error rates in data synchronization. For example, when a patient monitoring system detects a life-threatening stimulus or arrhythmia, the response immediate alert delivery to clinicians must meet response measures of less than 500 milliseconds latency to enable timely intervention. Similarly, during mass casualty incidents, the system's response to stimulus data requests might be measured throughout 1,000 requests per second to ensure care continuity. These metrics anchor performance goals, ensuring architecture aligns with clinical priorities like patient safety, regulatory compliance, and operational resilience. So, sample concrete performance scenario. Let's look into this in the same clinical example fashion. In normal clinical operations, users such as physicians, nurses, or lab technicians initiate transactions as part of daily workflows. For example, retrieving patients' electronic health record, as mentioned earlier, during the consultation, updating medication results, or submitting lab orders. Here, the source is clinicians generating the request, and the stimulus is transaction itself, such as querying a patient's allergy history or saving a new treatment plan. The artifact, the system component handling this transaction, might be a relational database optimized for fast read write operations, a RESTful API serving EHR data, or front end interface rendering patient dashboards. Under typical loads, these artifacts are designed to prioritize efficiency. For instance, databases may use indexing to accelerate search queries, while APIs employ rate limiting to prevent overuse even during normal operations. Performance hinges on balancing concurrency, multiple clinicians accessing the same patient's record, with responsiveness ensuring seamless workflows without delays that could disrupt the care. Goal for performance tactics. Tactics to control performance have their goals to generate response to an event, arriving at a system with some time based constraint. The response to these transactions include actions like displaying patient data, confirming successful updates, and flagging drug interactions in real time. Response measures in the context are stringent. EHR retrieval might require less than 1 second latency to avoid interrupting clinician patient interactions. While transaction success rate is 99.9% uptime, ensure reliability. The environment during normal operations assumes stable network conditions, predictable user loads, and compliance with baseline security protocols. TLS encryption for data in transit. However, visibility and variability persists. A primary care clinic with steady patient flow demands consistent performance, whereas hospitals' morning rounds might be brief spikes in concurrent users. Architects mitigate these variations through horizontal scaling, adding application servers during peak hours, and fault tolerant designs, redundant databases. Monitoring tools track metrics like CPU utilization, query throughout, and throughput, ensuring the system remains within defined performance thresholds even as routine transactions test its foundational resilience. The baseline performance during normal operations also informs capacity planning for stress scenarios such as pandemic surges, where the same artifacts must scale exponentially without degradation. So, these are the few tactics. Event arrives, tactics to control performance happens, response generated within the constraints as I just mentioned earlier. The performance tactics has controlled resource demand, managed resources. As I just mentioned that when event arrives, all the performance matrix applied as mentioned earlier to help you understand in more depth. Control resource demand. Let's look into this with our running example. In clinical architectures, as mentioned earlier, controlling resource demand is critical to prevent bottlenecks during high priority tasks, such as real time patient monitoring or emergency data retrieval. For example, when clinicians concurrently access EHRs during morning rounds, and the resource demands such as database connections, network bandwidth, and CPU cycles must be managed to avoid degradation. As mentioned earlier, techniques like rate limiting non-urgent background tasks such as batch reporting or analytics ensure that clinical transactions as well as critical transactions such as retrieving patients' current medication list receive priority. Caching frequently accessed data such as recent lab results or patient demographics reduces redundant database queries, lowering demand on storage subsystems. Additionally, concurrency controls like connections pooling and or thread prioritization prevent resource exhaustion when hundreds of users simultaneously update records. For instance, an ICU monitoring system might allocate more compute resources to real-time vital signs processing than to historical data, achieving dynamically adjusting based or clinical urgency. So if we carry on this example to understand more, the resource demand in clinical systems fluctuates with operational contexts such as surges in emergency admissions or scheduled maintenance periods. Auto-scaling cloud instances or containerized microservices can dynamically allocate resources during peak loads. For example, spinning up additional API servers when telehealth consultations spike. Load balancers distribute requests across servers, preventing overloading of a single artifact. Centralized authentication service is an example. However, environmental constraints such as legacy on premise hardware in rural clinics may limit scalability, non necessitating hybrid architectures that offload intensive tasks to the cloud while keeping sensitive data localized. Queuing systems handle asynchronous workloads like image uploads or AI driven diagnostic, decoupling them from time sensitive workflows. For example, a lab system might queue non urgent genomic data processing overnight to free daytime resources for the stat test results. Monitoring tools track metrics like memory usage and request latency, triggering alerts or automated scaling. Policies, when predefined thresholds such as 80% CPU utilization, are breached. By proactively managing resource demand, clinical systems maintain performance without compromising compliance or patient safety, even amid unpredictable operational demand. So, now let's look into how the resources are managed. Effective resource management in clinical systems ensure that critical infrastructure such as servers, databases, and network bandwidth is optimally allocated to meet dynamic demands. For example, during peak hours, a hospital, hundreds of clinicians may simultaneously access electronic health records or EHRs, requiring load balancers to distribute requests across multiple servers. To prevent overloading a single node, database resources such as read replicas or in memory caches can be strategically deployed to offload primary systems handling real time transactions like updating patient vitals or processing lab orders. Resource pools such as connection threads or GPU clusters for AI diagnostics are sized and scaled based on historical usage patterns and predicted spikes such as seasonal flu outbreaks. Prioritization policies ensure life critical tasks such as emergency room admissions or ICU alerts receive dedicated resources, while non urgent tasks such as batch billing reports are deferred or throttled. This proactive management prevents resource contention and ensuring consistent performance even during high stress scenarios like code blue events or mass casualty incidents. So, in the heterogeneous clinical environments, resource management often involves hybrid strategies to address infrastructure limitations. For instance, rural clinics with limited on premises server might leverage cloud bursting to handle sudden surges in telehealth demand while keeping sensitive patients' data localized for compliance. Container orchestration tools like Kubernetes dynamically scale microservices such as prescription validation or image analysis based on real time metrics like CPU usage or request queues. Legacy systems such as MRI machines with proprietary software may require dedicated virtual machines to isolate their resource consumption for modern cloud native workflows. Additionally, resources reservation techniques guarantee baseline capacity for essential services. For example, reserving bandwidth for real time video consultations ensure uninterrupted patients provider communication. Monitoring tools track resource utilization trends, enabling predictive scaling such as pre allocating extra compute nodes ahead of scheduled EHR upgrades or seasonal peaks. By balancing cost, compliance, and performance, clinical architects ensure resources align with both operational needs and patient safety imperatives, even in resource constrained or highly regulated environments. So let's look into design checklists for performance, allocation of responsibilities. Determine the system's responsibilities that will involve heavy loading. Have time critical response requirements are heavily used or impact portions of the system where heavy loads are or time critical events occur. For those responsibilities, identify processing requirements of each responsibility and determine whether they may cause bottlenecks. Additional responsibilities to recognize and process requests appropriately, including responsibilities that result from thread of control crossing process or process boundaries. I suggest you to pause this and look at this very carefully, and we'll go from here to the next. The next is coordination model. Determine the elements of the system that must coordinate with each other directly or indirectly, and choose communication and coordination mechanism that supports any introduced concurrency, ensures that required performance response can be delivered, can capture periodic, stochastic, or sporadic events arrival as needed, have the appropriate properties of the communication mechanisms. Data model, as we have discussed earlier, I would suggest you look into that with your running example in terms of understanding how data model behaves when we are dealing with a clinical system, and how the doctors, the patients, administrators, the clinicians, the nurses, and or some sort of consultants are dealing with that system, and what data model is suitable for them. Mapping among architectural events. Let's look into this with our running example. In clinical architectures, as mentioned earlier, mapping relationships among architectural events, such as linking a source, such as a clinician requesting a patient's EHR, to a stimulus, high priority data retrieval, the affected artifact distributed database or caching layer, and the environment peak hour network congestion ensures traceability between performance triggers and systems behavior. For instance, a sudden surge in telehealth requests, which is stimulus, from rural clinics, which is a source, might strain API gateways, which are the artifacts operating in the bandwidth constrained environment, prompting predefined responses like auto scaling, cloud resources, or rerouting traffic to edge nodes. The resource management, we have done an extensive discussion on this, so I will skip the slide. I would suggest you to look into this and read the associated chapter. Design checklist has binding time for each element that will be bound after compile time determines the time necessary to complete the binding. Additional overhead introduced by using the late binding mechanism. Ensure that these values do not pose unacceptable performance penalties on the system. Choice of technology. Again, choice of technology is significant. Will your choice of technology let you set and meet the hard real-time deadlines? Do you know its characteristics under the load and limits, as we have discussed that in the clinical system? We must be mindful on scheduling policies for reducing demand, allocation of portions that technology to processors is taken care. Other performance related parameters. Does your choice of technology introduce excessive overhead or heavily used operations? That's the question you should ponder upon. Performance is about management of system resources in the face of particular types of demand to achieve acceptable timing behavior. Performance can be measured in terms of throughput and latency for both interactive and embedded real-time systems. Performance can be improved by reducing demand or by managing resources more appropriately. So hopefully this has given you some more understanding of why performance is important, and our clinical system example gives you a more understanding that how we can work with it within a certain domain. Happy learning.